So, welcome back to this second half of today's lecture. We have seen some properties of the spectrum, and now I want to give some examples. How do we, and also why did we use the term spectrum, or why did people chose to use the term spectrum. Spectrum was already there in because spectrum in physics was studied long back, and it was there. Okay, so first of all, one more thing I forgot. So if I have a commutative ring A, and if I have this X is a spectrum, so if you take any X in X, that corresponds to Px, right, the prime ideal. So when is it close point? Close point means, so when is singleton X close? That is, when is X equal to X closure? Answer is very nice. This is if and only if Px is a maximal ideal. That is very easy, because suppose it is close, then what is Vpx? We saw in earlier part, this Vpx is precisely the closure of this singleton X. That is very clear, because this is close and this contains X, therefore this containment is clear, because it is a closed set and this is the smallest closed set. But on the other hand, this one contains X, therefore, so equality here. When will the equality happen? Sorry, when will the equality will happen? When there is no more point. There is no more point than X. That means there is Px has to be a maximal ideal, because if Px is not maximal, Px will be contained in some maximal ideal, and this Vpx will at least have 2 points. So therefore this is clear. I would still insist that you check here that it is correct. Closure of, so we have to check this, closure of X is precisely Vpx, that we have noted in the earlier discussion also. So when it is a close point, the P has to be a maximal ideal, otherwise this will have more points. Alright, so therefore if you remember, I denoted this maximal spectrum by X0. This is precisely the set of all close points in the topological space X. Alright, so now the example that I was, what I was saying, example. Let us start with a finite dimensional vector space over a field K. So let V be a finite dimensional vector space over a field K, and F be a linear operator on V, K linear operator on V. We will also write that is F belongs to endomorphisms of the K vector space V. This is a ring. This endomorphism is, you can add two linear operators by adding pointwise, and you can compose them, and with that it becomes a ring. Unfortunately, this is almost never commutative, not commutative if dimension of V as a K vector space is at least 2. But that does not matter for us, and in functional analysis or in physics also there is a study of linear operators, and for linear operators we have attached finite set, a finite subset of the field K, which is called a spectrum, which is actually called an eigenspectrum. This is finite dimensional. If the vector space is not finite dimensional, eigenvalues make sense, but characteristic polynomial does not make sense. So, let me recall the notation. For a linear operator f, we have this characteristic polynomial of f. This is a monic polynomial, and the dimension, the degree of this monic polynomial is the dimension of the vector space. So, this is x power n plus a n minus 1 x power n minus 1 plus a 0. This is the characteristic polynomial, coefficients are in K. By definition, it is actually chi f is actually determinant of this operator x idv minus f. So, you write down the matrix of f. So, I am sloppy in the notation here, I should have written matrix of f. Matrix of f with respect to some basis, and this determinant will not depend on the choice of that basis, and then you can see it's the monic polynomial of degree n, where n is the dimension of V. Alright, now what do the Cayley-Hamilton theorem says? Cayley-Hamilton theorem says that the zeros of the characteristic polynomial in K are precisely, these are the zeros, these are precisely the eigenvalues of the operator f. That means, this is precisely the set of all lambda in K such that there exists a non-zero x with f of x equal to lambda x. So, those are the eigenvalues. Now, alright. So, but on the other hand we recall the minimal polynomial. What is the minimal polynomial of f? For that you look at the evaluation map from the polynomial ring in one variable over K. This is the evaluation map into the endomorphism ring of this, where this is a K algebra homomorphism. So, I only have to give values on K. So, this is x going to f. This is an algebra and this was an element there. So, to define a map from the K algebra homomorphism from the polynomial ring to this algebra, I just have to give values on x. This is K algebra homomorphism. And what is the image of this? Image of this is the sub algebra of this endomorphism algebra generated by f. So, it is Kf. But now this is not commutative, but this is commutative because f commutes with itself. This is commutative, and this map is surjective. Image is this. So, in particular this Kf by isomorphism theorem, this is isomorphic to Kx modulo the kernel of this evaluation map. Note that kernel of evaluation map is non-zero. This is non-zero because this kernel will always contain the characteristic polynomial chi f. This is precisely the Cayley-Hamilton theorem. So this kernel is a ideal, non-zero ideal in this polynomial algebra over a field. Therefore, it is generated by a single, it is a PID. Therefore, kernel is non-zero, so it is generated by a monic polynomial, uniquely determined, and that minimal, that is called the minimal polynomial of the operator f. So, this is generated by mu f, where this mu f is called minimal, the monic minimal polynomial of f over k. That is the definition of minimal polynomial. But this chi f belong there means what? That means mu f divides chi f in kx. But this is not, this is still crude relation. What is the right relation is, they have moreover, this is a non-trivial, not very difficult but easy and interesting, many applications of this theorem. What I say, mu f and chi f have the same prime factors. Multiplicities may be different, but if you have a prime factor of mu, then it is a prime factor of chi, and if you have a prime factor of chi, then it is a prime factor of mu. This is in particular they have the same zeros. So, Vk mu f equal to Vk chi f. And what does mean by that they have same prime factors? That means, so I will write, I will spell out this. That means if chi f equal to pi 1 power r1, or let me call it nu, because I want to, pi 1 power nu 1, pi r power nu r, where 0 less bigger than nu I. I is from 1 to r, and pi 1 to pi i's are prime polynomials and distinct. Then mu f has to be of the form pi 1 power mu 1, pi r power mu r with 0 strictly less than mu I less equal to nu I for all I. So, if pi I occurs here, pi I also occurs here, but the multiplicity may be smaller, that smaller because it is divided. So, now what am I doing, what do I want to explain you? So, what is our ring now? Our ring is, consider kx modulo the ideal generated by mu f, and this is, we know the K algebra, this is isomorphic to kf, and if I call this as A, what is the spec of A? Spec of A is precisely this pi 1 to pi r. I mean the ideal generated by pi 1 and 2 pi r. Because they are prime polynomials, these are the prime ideals, and that is the spectrum. And in particular, when pi 1 is linear, for example, that will give you eigenvalues. So, this is, so in particular, if you consider the field equal to C, algebraically closed, then these pi i's are linear polynomials because they are irreducible polynomials, prime polynomials in Cx, they are linear. Then spec of A is precisely this. On one our notation is x1 minus lambda 1 x, not x1, x minus lambda r, these are r ones, and these we are identifying, this set we are identifying with lambda 1 to lambda r, which is a subset of C, a finite subset of C. This is called spectrum. This is called spectrum of F. Spectrum. This is called eigenspectrum, to be very precise. This term was used in physics, and therefore that matches with our spectrum, and that was the reason why people have started using this terminology. All right, so some more examples. So next example, example. All right, so suppose let A be a ring, commutative always. Let us assume it is Artinian. Assume that A is Artinian. And we approved long back, we approved a result which says that a ring is commutative ring is Artinian if and only if A is Noetherian and every prime ideal is maximal. Not only that, moreover we have also proved, moreover this every prime ideal is maximal means spec of A equal to SPM of A, and it is a finite set. That is what we have proved earlier, that it has finitely many maximal ideals and every prime ideal is maximal, therefore spectrum is also finite, and that means this is a finite set of points. So this X is a finite topological space, that is X is a finite topological space and we have also know that each X in X is a closed point because it is maximal ideal. We have noted maximal ideals are precisely the closed points. So that means singletons are closed, but then therefore X is a Hausdorff space, topological space, because finite, therefore each point is closed, therefore each point is also open, and therefore it is actually discrete space, in fact discrete topological space. See, this is how the algebraic geometry will always go on, commutative algebra to geometry, geometry to algebra. All right, so all right, so some more observations I want to write it down, maybe for future use. All right. So, this should be let me call it a proposition. Alright, so let A be a Noetherian ring. Then A has finitely many minimal prime ideals. Okay, proof. Note that when I say finitely minimal prime ideals, that means we are considering this ordered set spec A with inclusion, and the minimal elements in this ordered set we keep calling minimal prime ideals. So, min of this set, and we want to show that this is a finite set. Alright, so recall that we have proved in the first half that if A is Noetherian, then this spec A is a Noetherian topological space. So, A Noetherian implies spec A is a Noetherian topological space. That means open sets form satisfy the ascending chain conditions, or it has the every non-empty subset of open sets has a minimal element, maximal element. The other way for the closed sets. Alright, so and we have also proved, when recall also we have proved that when X is a Noetherian topological space, then it has finitely many irreducible components, implies X has finitely many irreducible components. What are irreducible? We have just said component means they are the maximal irreducible closed subsets. So, that means X is a union of the irreducible component. So, that is, let me call it V1 union VR, where VI's are irreducible components, that is maximal irreducible subsets. So, they are in particular they are closed. So, they are closed and irreducible, and therefore, just now we have noted that these each Vi will correspond to the prime ideals. So, this V1 will be V of P1 and this VR will be V of PR, where P1 to PR are prime ideals in the ring A, and this irreducible component means maximal irreducible subsets. But if they are maximal, then this P1 to PR has to be the minimal primes, because if they are not minimal, if any one of them is not minimal, then it will contain further a prime ideal properly. But then this, if for example, if Q is a prime ideal with Q contained in P1 not equal to, let us say, then what will happen? Then apply V. So, V of Q will become strictly bigger than V of P1. Both are radical ideals. Therefore, applying V, they cannot become equal. Formal notation thus will tell that they are proper. So, this cannot be maximally irreducible, because this is already irreducible, because it is a prime ideal. Therefore, this is irreducible and it contains properly this. So, this cannot happen. So, equality here, therefore, equality here, therefore, P1 is minimal. Similarly, P1, P2, PR etc. are minimal, and therefore, that proves that it has finitely many minimal prime ideals. This is very important proposition. Alright. So, with this I will only make one comment which also is very important to understand topological arguments, namely, so see, if you have a topological space X and suppose it is X is spec A, then we know already the irreducible component. This X is a union of Vp1 union Vpr. These are P1 to PR are the minimal prime ideals. So, this set is precisely the min spec A with respect to the inclusion. Okay, irreducible, these are irreducible component. And now, what is the relation between connected subsets and irreducible subsets? So, irreducible is more stronger condition. So, therefore, what we have to note is every connected component. So, every connected component of X equal to spec A is a union of sum of irreducible components. Because every irreducible subset is a connected subset. So, this is what I wanted to write as a corollary. So, if you try to draw a picture, if A is a commutative ring and X is spec A, I will try to show you by picture. So, and P is the prime ideal. So, X is a point here. So, that is this X closure will be this irreducible subset, closure of X. If you take another one, it will be closure of Y. If they intersect, they are still connected. So, you will have to find components, irreducible components which do not intersect, and that will form a disconnected. So, that is how this. So, now all these getting more and more intimater with the topology and commutative algebra. So, this is a beginning actually, but unfortunately we cannot go on so much in this course. In the next time I am going to start a new topic that also has a geometric content, but first I will have to digress on the algebraic component, what is called integral extensions of the rings, and then what happens to the spectrum. So, this is what the topic I will take it, and this will be the last topic of this course. Okay, with this I will stop and we will continue our lecture in the next time. Thank you very much.